Hello everyone, I'm Yuwei from Cornell. Now I'm going to present FeatGraph, a flexible and efficient backend for graph neural network systems. This work is in collaboration with Amazon Web Services. To start with, graph neural networks are getting popular in recent years. As we know, graph is an important data structure. It's a universal language to describe connections and relations. A lot of interesting problems deal with graph. So one question people ask is, can we apply deep learning to graph? While traditional deep learning models such as convolutional neural network and recurrent neural network have achieved huge success in processing images and sequential data, they cannot handle graph. In order to extend deep learning to graph, people propose graph neural networks, GNN. This research area is quickly developing, and we see more and more successful applications of graph neural networks, such as recommender systems and molecular analysis. Driven by this trend, specialized systems are emerging to simplify the development of GNN models, such as Deep Graph Library, PyTorch Geometric, and PyTorch Graph Learning. Now, let's look at how GNN works. The key building block is message aggregation. Message aggregation is composed of two parts. The message function calculates a message from the feature of each source vertex. In GNN, each vertex is associated with a feature tensor or a feature vector in common cases. Second, the aggregation function aggregates the messages as the new feature of the destination vertex. The figure here shows a concrete example. We see a graph of 4 vertices and 3 edges. A is the destination vertex, B, C, D are the 3 source vertices. Initially, each source vertex is associated with a feature vector of length 2. The message function in this example is multilayer perceptron, MLP. We apply MLP to each source vertex to generate a message, which is a vector of length 4. Then we aggregate the messages by taking the max of them. We use the aggregated message as a new feature of vertex A. That message aggregation, note that both the message function and the aggregation function are customizable. Different GNN models use different message functions and aggregation functions. Another key building block of GNN is attention calculation. In simple GNN models, there is no weight on the edge. It's just a binary value denoting the existence of edge. In advanced GNN models, in order to improve the model's expressiveness, every edge is assigned a weight. The weight is learnable using some attention mechanism. Attention calculation is described by an edge function. The figure here shows an example of dot product attention. The edge function performs a dot product between the source vertex feature and the destination vertex feature, and it generates an attention score on the edge. Same here, the edge function is customizable. Dot product is just one of them. Okay, that's the key building blocks of GNN, message aggregation and attention calculation. Now I'm going to show you that GNN workloads impose huge challenges to computing, and I will explain why existing solutions are not sufficient. Most of the GNN systems are built on existing deep learning systems. For example, PyTorch Geometric uses PyTorch. DGL supports both PyTorch and MSNet. On top of the tensor abstraction of the deep learning frameworks, the GNN system provides a graph abstraction to make programming easier. However, in the backend, we still rely on deep learning frameworks to do the computation. As we know, deep learning frameworks optimize for computation of dense tensors, and they don't have sufficient support for graph computation, which is highly sparse. I will talk about the sparse nature of graph computation in more detail later. So, the problem of using deep learning frameworks as a backend has been acknowledged by the developers of GNN systems. To solve the problem, the DGL team has proposed to use existing graph processing frameworks as a backend. Graph processing is a pretty mature research field. People have built a lot of graph processing frameworks. They are pretty flexible. They can easily express the building blocks of GNN models, which is good. The challenge is that these graph processing frameworks are not efficient in handling GNN workloads. They are designed for traditional graph workloads like BFS or PageRank. In these traditional graph workloads, each vertex and edge is associated with a scalar, but in the case of GNN models, it's a feature tensor. As a consequence, GNN workloads have much more complex vertex-wise and edge-wise computation, and traditional graph workloads. Let's look at a concrete example. Suppose we want to run MLP message aggregation in parallel on GPUs. How would it be parallelized by existing graph processing frameworks? Well, existing graph processing frameworks exploit edge parallelism by scheduling the computation on one edge to one thread. The underlying assumption is that the computation on every edge is lightweight. That is true for traditional graph workloads. Think about UDFs and PageRank. It's all about graph traversal, right? But that assumption breaks in the case of GNN workloads. As we see here, every edge performs an MLP, which itself provides abundant parallelism. So we want to exploit the parallelism in feature dimension, in addition to parallelism in the graph topology. We propose FeatGraph. FeatGraph co-optimizes graph traversal and feature dimension computation. By doing so, FeatGraph accelerates GNN training and inference by 32x on CPU and 7x on GPU. This is the system overview of FeatGraph. At the top level, users train GNN models in specialized systems such as DGL and PyTorch geometric. FeatGraph serves as a backend for these systems. FeatGraph provides a flexible programming interface. It decomposes a kernel specification into two parts: sparse templates and UDFs, user-defined functions. The sparse templates express graph traversal, and the UDFs express feature dimension computation. This programming interface enables decoupled two-level optimizations. After performing optimizations for both the sparse templates and the UDFs, FeatGraph uses TVM to generate kernel code for both CPU and GPU. TVM is a deep learning compiler. It handles dense workloads. FeatGraph extends TVM to support the sparse patterns of GNN workloads. In the next few slides, I will first talk about the programming interface of FeatGraph, specifically how to map graph computation to sparse kernels. Then I will talk about the optimization techniques. There is a strong connection between graph computation and sparse kernels. On the left is the graph view of message aggregation. In this example, the message function just copies the feature vector of the source vertex, and aggregation function is sum. From a matrix view, as shown on the right, this is doing SPMM, sparse dense matrix multiplication. The sparse matrix is the adjacency matrix of the graph. The dense matrix is composed of the feature vectors. So we see that when the message function is copied and the aggregation function is sum, message aggregation is mapped to SPMM. In general cases, since the message function and the aggregation function are customizable, we have a generalized SPMM. This slide shows that dot product attention is mapped to SDDMM, sampled dense matrix multiplication. SDDMM multiplies two dense matrices, followed by an element-wise multiplication with a sparse matrix to output a sparse matrix. Same here, since the attention calculation is customizable, we see that it's mapped to a generalized SDDMM. Okay, we see that the building blocks of GNN models can be mapped to generalized SPMM and SDDMM. In addition, the gradient calculation of GNN models is also mapped to these two kernels. So these two kernels are important to both the training and inference of GNN. How do we express generalized SPMM and SDDMM kernels in FeatGraph? In FeatGraph, we express a kernel by composing sparse templates with user-defined functions. This slide shows the programming interface. The SPMM template takes in 5 arguments: the adjacency matrix of the graph, the user-defined message function, the user-defined aggregation function, the target, which is either CPU or GPU, and the feature dimension schedule, FDS, which specifies optimizations for feature dimension computation. I will talk about FDS in detail later. FeatGraph also provides the SDDMM template, which takes in 4 arguments: the adjacency matrix of the graph, the user-defined edge function, the target, and the FDS. Let's look at a concrete example of expressing GCN message aggregation in FeatGraph. We use the SPMM template. The message function copies the feature vector of the source vertex, is written in TVM. The aggregation function is sum. We trigger the SPMM template with the message function and the aggregation function. Essentially, GCN message aggregation is mapped to a vanilla SPMM. Now let's look at how to optimize it on CPU. Graph processing on CPU is known to be challenging, and the biggest problem is low cache utilization. Prior works try to improve locality in graph traversal by doing graph partitioning. One method is 1D partitioning, which partitions the source vertices. Assume the cache capacity is able to hold 2 vertices. 1D partitioning then partitions the 8 vertices into 4 segments so that each segment fits into the cache. This improves the read locality within each segment. The cost is that it needs to merge intermediate results from different segments. This method works well for traditional graph applications such as PageRank, but it's no longer effective in the case of GNN workloads. With the feature dimension, we need to partition the graph into too many segments, making the cost of merge too large. To address this problem, we propose combining graph partitioning with feature dimension tiling. As shown in the figure, feature dimension tiling reduces the merge cost by 50%. But the drawback is that it needs to traverse the adjacency matrix twice. Feature dimension tiling introduces a trade-off between accesses to graph topological data and accesses to the feature data. When the tiling factor is properly selected, feature dimension tiling can improve the performance. Now let's look at how FeatGraph applies the mentioned optimization techniques. We call it decoupled two-level optimizations. Specifically, FeatGraph incorporates graph partitioning into the sparse template, and it allows the user to specify feature dimension tiling with an FDS, feature dimension schedule. As shown in the code, the FDS splits the feature dimension by a factor of 8. The split factor is tunable. More complex UDFs that compute on multi-dimensional feature tensors may require a multi-level tiling scheme, which can also be expressed by the FDS. We evaluated the effect of graph partitioning and feature dimension tiling. The figure shows the results on the Reddit dataset under different feature lenses. As we can see, combining graph partitioning and feature tiling effectively boosts the performance. Specifically, when the feature length is 512, feature dimension tiling alone brings 1.2x speedup. Graph partitioning alone brings 1.7x speedup. Combining them together achieves 2.2x speedup. We also analyze the sensitivity of the performance to partitioning factors. As we see from the figure, the best performance is achieved with 16 graph partitions and 4 feature partitions. In this work, we use naive grid search to find the optimal partitioning factors. Using intelligent tuners is left for future work. Now let's look at optimizations on GPU. We use dot product attention as the example, which is mapped to a vanilla SDDMM. As we know, GPUs have massive parallel compute capacity, so effective parallelization is the key to achieving high performance on GPU. FeatGraph exploits parallelism in the feature dimension. The strategy is that multiple threads collectively process one edge using tree reduction, as shown in the figure. In comparison, the parallelization strategy in Gunrock is that one thread processes the entire edge. As I have mentioned, existing graph processing frameworks, including Gunrock, are not aware of the feature dimension, so they cannot exploit parallelism in the feature dimension. This slide shows how FeatGraph applies the GPU optimization techniques, same as on CPU. It does decoupled two-level optimizations. It incorporates vertex or edge parallelization into the sparse templates, and it allows the user to specify feature parallelization with an FDS. As shown in the code, the FDS applies tree reduction on the feature dimension. If we have a more complex user-defined function that computes on multi-dimensional feature tensors, we may require a multi-level parallelization scheme, which can also be expressed by the FDS. This slide evaluates the effect of feature dimension tree reduction. The figure shows the results on a synthetic random data set. As we can see, tree reduction is especially efficient when the feature length is large. The naive parallelization strategy in GNRock, which assigns the entire feature vector to one thread, is not efficient in handling large feature length because each thread consumes too many registers. Okay, putting it all together, this slide shows how we express and optimize MLP message aggregation in FeatGraph. Don't read the code. I just want to convince you that FeatGraph is powerful enough to handle complex kernels like MLP message aggregation. We evaluate FeatGraph on AWS EC2 instance. We tested 3 kernels: GCN message aggregation, which is mapped to vanilla SPMM, MLP message aggregation, which is mapped to a generalized SPMM, and dot product attention, which is mapped to a vanilla SDD-MM. In compare with vendor-provided sparse libraries, specifically MKL on CPU and coarse-grained on GPU. These libraries are highly optimized, but they are not flexible. They can only support a subset of the kernel. We also compare FeatGraph with graph processing frameworks, specifically Lagra on CPU and GNRock on GPU. This slide shows the single-threaded CPU kernel performance on the Reddit dataset. For all the figures, the x-axis is the feature length, the y-axis is the execution time. Lower is better. As we can see, FeatGraph outperforms both Lagra and MKL. MKL doesn't support MLP message aggregation and dot product attention. FeatGraph achieves similar speedup on other tested datasets. This slide shows the multi-threaded CPU kernel performance evaluated on the Reddit dataset with feature length 512. The x-axis is the number of threads. The y-axis is the speed up over single-threaded execution. As we can see, FeatGraph achieves better scalability than both MKL and Lagra. FeatGraph scales well because of 2 reasons. First, it avoids last-level cache contention by assigning multiple threads to work on one graph partition at a time. Second, the thread pool in TVM runtime is lightweight and efficient. This slide shows the GPU kernel performance on the Reddit dataset. We can see that FeatGraph outperforms GNRock in all the 3 kernels. FeatGraph is on par with coarse-grained on the GCN message aggregation kernel. coarse-grained doesn't support the other 2 kernels. We noticed that GNRock is extremely slow on the message aggregation kernels. That's because of 2 reasons. First, its edge parallelization incurs a huge overhead of atomic operations for vertex-wise reductions. Second, it doesn't exploit parallelism in the feature dimension computation. This slide shows the results of end-to-end GNN training and inference. We integrated FeatGraph into DGL version 0.4. The original backend of DGL is a mini version of GNRock. We tested 3 GNN models: Graph, Sage, GCN, and GAT. As we can see from the table, FeatGraph accelerates end-to-end GNN training and inference by up to 32x on CPU and 7x on GPU. The highest speedup is achieved on the GAT mode, which has a more complex architecture than GCN and GraphSage. FeatGraph is available on GitHub. Welcome to try it. That concludes my presentation. Thank you.